Now, we are entering something really complicated in our function journey. We call this a power function sum. This function combines multiple power terms to create kind of complex behavior that can model a lot of rich real-world phenomena. Look at the general form, y equal to ax cubed plus bx squared plus c. This isn't just one type of behavior. This is kind of like a behavior where every term has a role to play. The x3 term provides a dominant long-term behavior. The s squared term adds some kind of curve and complexity. And the constant term can shift everything vertically. Now, if you look at what happens when x less than 0, you notice how things can change. When a is more than 0, we have the characteristic shape that starts low on the left, rises through the middle, and then shoot outwards on the right. When a less than 0, the entire behavior flips. It starts high on the left, and then it plunges to the right. And what makes all this function fascinating is that they seem to have multiple turning points. Unlike our simple cubic function that have smooth S-curve, this power sum can have some kind of wave, peaks, and valley. They can use to model complex phenomena like economic cycles, population dynamic with multiple growth phases, or engineering stress patterns. You look at the left curve showing x cubed minus x squared. The red curve represents x cubed. The blue curve represents negative x squared, and the green curve shows the final sum. Notice how the final result isn't just a single combination. It's kind of like a new function with its own unique characteristic. The cubic term dominates for large value, but the quadratic term has some interesting local behavior in the middle term. If you look at the right term, it shows x cubed plus x squared, where both terms act together instead of opposing each other. Notice how the blue quadratic curve adds to the red cubic curve to create the green sum, the green curve that has different curvature property. Notice when we add function, we are literally just adding the y value at each x coordinate. Where x3 might give us a value of 8 and x squared might give us a 4, the sum will give us x cubed plus x squared equal to 12 at that point. So this interaction between terms can create unexpected behavior. The sum might not just be like a cubic light or quadratic light. You can see turning point, inflection point, and region 1 when the terms dominate over another. The insight here is that a lot of complex behavior emerge from the interaction of similar components. So if we can understand how the individual function behave, we can predict and analyze how the combination will perform. To summarize, as again, the coefficient A is like the master controller. It has the authority over the function overall behavior. It determines the steepness, determine whether you get the standard S shape flowing from bottom left to top right, or the inverted S shape. Once you know the sign and magnitude, you know how the fundamental behavior will dominate as S get larger. For constant C, it is kind of like a positioning term. It's simple to understand, and the value of C determines exactly where your curve crosses the y-axis. Positive C lifts the entire function upwards, negative C push it downwards. Practically speaking, you can think of it as a starting condition or the baseline value. If you are modeling population growth, C might be your initial population. If you're modeling profit, C might be your fixed cost.
Smash your maths exams. Download Learn Maths Today for real exam questions and achieve top marks.